Ну, в общем, сейчас должно быть вроде. Ну, или оно там через... Там же задержка какая-то. Это... А, идет, да? Ну, понятно. Ну, я не знаю, как это лечить.
Ну, ладно, потом.
Ой?
А, нет, еще нормально.
Okay.
Nobody else. Okay, so let's start our seminar. First, Dean, you know, I met him, I told him, but okay. So today we're going to welcome Timothy Anson, if it's correct. Yeah. He's a postdoc at the Institute for Theoretical Mathematical Physics in Moscow. So he will tell us today on disforming the Kerr metric.
Yes, thank you. So I hope everyone can hear me online. So today I'll be presenting some work I did during my PhD. During well, a bit more than a year ago, actually. The first paper that I'm going to present came out in June of 2020. So I've kind of put this project aside for a few months, writing my thesis and things like that, but I'm planning to come back on some of the issues that I will present during this talk. So yeah, it's work that I did with my PhD advisor, Evgeny Ivanichev, and Christos Chalmousis. So I don't know if it's necessary to motivate the how much black holes are interesting. I mean, we have more and more evidence as the years pass that these objects actually exist in nature, whether it be from the observation of stars around Sagittarius A star, that's been going on for almost 30 years, or more recently, the detection of gravitational waves coming from binary black hole system, or even with neutron stars more recently, or the imaging of Messier 87 star black hole, which I put a picture of here, by the Event Horizon Telescope collaboration. Basically shows that black hole physics is a very important topic at the moment. And in GR and general relativity, rotating black holes are described by the Kerr metric. And I'll be reviewing some of the main properties of this solution in the talk. But I'll then be more focused on black hole solution in modified gravity, namely scalar tensor theories of gravity. And studying such objects as alternatives to the Kerr metric provide a way both to test general relativity, but also maybe to predict some effects of modified gravity, as we'll see in a moment. And the usual approach to construct such deformations of the Kerr spacetime in the literature is to use what I call ad hoc deformations, which is basically, from a theory agnostic point of view, just change some components of the metric in order to obtain some experimental signatures. But you don't know the theory which underlies the objects are solution of. It's just some manual deformations of the spacetime. So on the other hand, what we propose is to, so using the disformal map, which I'll present, one can construct deformations of the Kerr metric, which are actually solutions to some scalar tensor theories. And I believe this is a nice feature, to actually know the theory that the objects solve. So the main context of what I'll be talking about, maybe for some who are not too familiar with this, is scalar tensor theories. So basically there's a theorem in GR, which is Lovelock's theorem, which states that if you stay in 4 dimension and construct a Lagrangian with the metric and only up to second derivatives, you're stuck with Einstein's field equations. So if you want to modify the physics, you have to break one of these hypotheses. The most common things to do is either to add more dimensions or add extra fields, whether it be scalar or vector or both. And the simplest extension in that regard is just to consider an additional scalar field which mediates the gravitational interaction. And these theories, so-called scalar tensor theories, have greatly evolved over the years, starting from Jordan theories. In the 70s, Horndeski wrote the most general action containing a scalar field, which leads to second-order Euler-Lagrange equations. But more recently, this was shown not to be a necessary condition because you can actually have higher-order field equations, or the Lagrange equations, which only propagate 3 degrees of freedom, namely the 2 coming from the graviton and 1 extra degree of freedom coming from the scalar. And having higher-order field equations is not dramatic as long as you impose some degeneracy conditions on the kinetic matrix of regression. So these theories are called degenerate higher-order scalar tensor theories or extended scalar tensor theories. We'll use the name of those. And basically, the Lagrangian looks like this. So the usual Einstein-Hilbert action, of course, is just the Ricci scalar R. And these functions that I wrote here depend on the scalar field phi, which we add, and the kinetic term of the scalar field x, which is d phi squared. So you can basically write an action like this. But as I said, in order to propagate only 3 degrees of freedom, you have to impose degeneracy conditions on these functions a1, a2, a3, a5. I won't go into details. Basically, this is just what the theories look like. So I'll be more focused on the actual properties of the solution we constructed. I'll start by reviewing some important aspects of the Kerr solution in GR. And then using the same logic, I'll go through the properties of
Excuse me, a question about the previous slide.
Yes.
In the selection properties, why do you select this Lagrange? Is it because it should include only 2 time derivatives?
Right. So this is
Equations of motion.
what's called the quadratic dose theory. So it's basically these 5 operators are the 5 that you can build that are quadratic in second-order derivatives of phi.
Yeah.
So you have basically, it's always like a second order in second derivatives. You can also build cubic theories and so on. But if you generically vary this, it will contain up to 4 derivatives of the scalar field.
Yeah, but 2 derivatives in respect to phi, right?
No, you can have more, because if you don't impose any conditions on these functions AI, you propagate Ricci-flat growth. So you have extra degrees of freedom.
Yeah.
If you don't impose any conditions, this is
so you impose some conditions to have only 2 derivatives in respect to phi, right?
Yeah.
4 derivatives in total, but 2 derivatives.
Yeah, basically, if you just vary the action, you get 4 derivatives, but you can redefine variables in order to have a system with 2 derivatives. So in the end, you only have, all the fields.
So it's kind of you redefine the field, like second field. The field is another field.
Well, basically what they showed is that it doesn't matter if when you just look at the first step, so you take this Lagrange and you have the Lagrange equations, they have 3 or 4 derivatives. So you can redefine, because the kinetic matrix is degenerate, here, you can redefine variables such that in the end, you can isolate 3 variables that propagate, you don't have any ghosts, basically. You don't have any extra degrees of freedom. But it's non-trivial. I went very fast, but of course these papers go into detail, and it's not a.
So it's kind of matrix in front. I just want to understand what is the selecting properties of these those theories. This as opposed to other.
Okay, so this one I wrote is called, so it's quadratic dose theories. So it's the most general Lagrangian containing basically second derivatives of phi squared. Right, so you get 2, so you have 5 ways to contract these to get 2 times second derivatives. So this is the most general. That's the starting point. And then you do the Hamiltonian analysis, which is non-trivial, and you put conditions on the AI, so that in the end you propagate no list.
Okay, so no general properties, just some conditions on AI.
Yeah, exactly. It's just some general, because what Horndeski did in the 70s is just so you have these 2 terms basically, A1, A2, and which have to be opposite and connected to the derivative of this function. And if you do that, even the first step, which is the Riemann equations, doesn't contain higher derivatives, and you don't have the ghost. But what they showed is you don't, this basically at the very first step, you can have higher derivatives, and it doesn't mean that you propagate a ghost. Basically, the Hornesi condition is sufficient, but not necessary. So they just tried to extend it. And also they studied cubic interactions. I mean, yeah, where you have cubic terms in second derivatives of phi. And people little by little try to extend this, but basically this is already a nice extension. This is what we're working with, but it's not like doesn't have any special properties. I don't know if you're looking for something really special. Just start with the most general thing, quadratic in second derivatives, and put conditions on the functions so that you have no ghost, basically. Osteographic. Okay. Right. So I'll start by reviewing Kerr, then describe the nice properties of our solution, and in the end, I'll briefly talk about the second paper we did about basically assuming that Sagittarius A star is a disformed black hole, and what does it mean for the orbital stars around the subject. Okay, so let's start from the basics, but maybe some of you are not so used to working with rotating black holes. So this is the Kerr solution, which is a solution of general relativity of vacuum, so its Ricci tensor is 0. And in the so-called Borel-Nyquist coordinates, which is the coordinate system which minimizes the number of diagonal components, this is the expression of the metric. So the functions rho and delta are commonly used. And as you see, there's only one off-diagonal component in this coordinate system, which is dt to phi, and this is where you get the rotation of the black hole. The parameter m is the black hole mass, and a is the spin. If you put a to 0, this drops out, and you just obtain the Schwarzschild metric in the usual Schwarzschild coordinate space. And very much like in the Schwarzschild case, you think that there's a singularity and it's delta equals 0, but it's actually just a coordinate singularity and not a curvature singularity. And you can actually write the metric actually in the original form written by Kerr, in which it's obvious that these points which solve this polynomial equals 0 are not singularities. But this coordinate system is useful because it minimizes the number of off-diagonal components. So even though this delta equals 0 is not a singularity, you can, for instance, by calculating the Fletchman scalar, you can see that when rho equals 0, so this equals 0, there is the so-called ring singularity of the Kerr metric, and this happens when both r is 0 and theta equals pi over 2. So this metric has many interesting symmetries. The most obvious ones are axisymmetry, meaning you have two commuting killing vectors dt and d phi. So in other words, the metric components don't depend on time and phi coordinates. And another interesting property, which is sometimes not even mentioned, is the so-called circularity. So in the coordinate system that I used here, the Borel-Nyquist coordinate system, it's obvious that if you simultaneously flip the time and phi components, the metric remains invariant. Okay, so under this change, the metric is invariant, and this can be expressed using this relation. So if you just lower the indices on these vectors here and calculate the Sledge product, these are the circularity conditions for the Kerr metric, and it shows that you can get a coordinate system where you perform this. And another very interesting property of Kerr is the existence of non-trivial killing tensor. Because if you generalize the Kerrian equation to order 2 tensors like this, you can actually find a non-trivial 2 tensor for the Kerr metric. And I say non-trivial because from this equation, if you can see that the metric itself is trivially a Kerrian tensor. Okay, if you take the Levi-G connection and replace A by G, obviously this is 0. So there exists a non-trivial Kerrian tensor. And basically, you can associate, whenever you have a Kerrian vector or tensor, you can find a constant of motion along geodesics. So usually we call this one the energy, this one the angular momentum. And okay, for the metric, it's just the mass of the particle. And for the Kerrian tensor, we don't really have an experimental interpretation, but it does provide a constant of motion, which then allows to separate the geodesic equation. By the way, the constant is Carter's constant. And in fact, Carter separated the geodesic equations for Kerr even before Other people made the link with the Killing tensor. Nowadays, it's easier to see it that way. And these four constants of motion allow you to separate the geodesic system. And hence the study of geodesics in the Kerr spacetime, even the Kerr-Newton spacetime, is greatly simplified. Now let me mention important hypersurfaces in the spacetime, because after I present the solution we built, I'll follow the same logic and this will be important. So let me just mention the main properties of Kerr. So let's consider stationary observers, which are observers lying at r and theta constant. So basically you can give them a forward velocity of this form, where omega is just some function. And if you ask for these observers to be time-like, you have to, this function omega must lie within these bounds. Okay? And so in the Kerr spacetime, when GTT becomes positive, this lower bound has to become positive. And basically, from the point of view of someone at infinity, a time-like observer which crosses this ergosphere has to be co-rotating with the black hole. So omega here has to be positive. And of course, inside this ergosphere, so in the ergo region, there are many energy extraction processes, and those processes are superradiants, which are often considered. And once you get to a point where this square root is not defined anymore, so this becomes 0, so you have to solve this equation. The outermost root verifying this is this one, which is exactly the outer horizon of the Kerr metric. So basically, the stationary observers have to be co-rotating inside the ergosphere and then just stop existing at the event horizon. So this is what happens schematically, basically. That's just what I said. So the static observers cease to exist inside the ergosphere, but can still be stationary in the sense that they can still rotate in the same direction of the black hole. And then here you can no longer solve this equation. And this is the outer horizon of the Kerr metric. And something else which is interesting about the Kerr black hole is comes from the so-called rigidity theorem by Hawking, which states that the event horizon for the Kerr solution is actually a Killing horizon. Meaning you can find a Killing field, which I wrote here, which has a vanishing norm on the outer event horizon, and which is also normal to it. And basically, this means that the outer horizon is Killing horizon. And this also works for the inner horizon, but we'll be interested in the outer horizon. And coming from this Killing vector, you can define by the non-affinity condition here, you can define what's called the surface gravity and imply what the Hawking temperature of the black hole is. So the thermodynamics, the study of the thermodynamics of black holes in the NGR is greatly simplified by this property of having a Killing horizon. Because you can show that in this case, the surface gravity is constant on the horizon. And so on. Okay, this is just a summary of what Kerr looks like. So in red, you have the ergosphere, and in black, the event horizon. And the shaded region in red here is the ergo region. And I didn't mention, but of course, you have an inner horizon, inner ergo surface, and the ring singularity here in dotted blue. So sorry if this was a bit long and basic, but it serves as an introduction to what we actually did that was new. So in the context of these scalar tensor theories, there's actually a solution which is called a stealth Kerr solution, which was constructed a few years ago. So stealth means that the solution for the metric in the theory is actually the same as GR. So in some sense, the scalar field is kind of hiding. There is a non-trivial scalar field, but it doesn't directly influence the metric components. So this is what the solution looks like. The metric is Kerr, and the scalar field has this form. And it's actually a geodesic direction, because you can show the kinetic term of the scalar field is constant in their construction. And after commuting second derivatives on the scalar field, you see that the gradient of phi here just defines the geodesic direction. So we have a solution where the metric is in scalar tensor theories, where the metric is Kerr, and we have a geodesic scalar, which is non-trivial on top of it. And then we use the fact that a certain class of these scalar tensor theories is invariant under the so-called disformal lattice. So the disformal map was introduced by Wittgenstein in the 90s, and is basically a generalization of the conformal map. So I believe most of you are familiar with conformal maps, and maybe even with disformal maps. So you basically add an extra piece here with which is proportional to the gradient of the scalar field. And what was shown a few years ago is that if you start with a theory belonging to this large 1A class, which Horndeski theories are a part of, by the way, and you do an invertible field redefinition in this form, you actually end up with another theory in the same class. So there's some stability of those class under this map. And then the procedure to obtain a theory that's not equivalent is to couple the matter fields to minimally to the resulting metric. So let me give more details. If you start from a dose theory here, S tilde, depending on this metric G tilde, as I just said, if you do this field redefinition, which is invertible, you end up with another action belonging to the dose class, expressed in terms of this new field G, right? But you may say, well, you've just redefined the fields, so you're just rewriting the theory in another way. Well, the difference comes from the coupling of matter. So if you started with a theory where the matter fields psi m here are minimally coupled to the metric G tilde, in the end, the equivalent action would be coupling the matter fields in the end to this complicated expression of G and phi, right? This would be strictly equivalent. But if in the end, once you've calculated your gravitational action here, if you couple the matter fields minimally to the new metric G, then you've obtained a theory that's not equivalent. Okay, so we're not just redefining fields. We actually, if we consider that the matter fields are minimally coupled to the new metric we obtain, then the physics can be different, and that's what we'll see. So this is what we have, basically. We considered a new metric called G tilde, which is the usual Kerr metric, and we shift it by a constant coefficient here. D and Q are constants. This is just one overall constant. I write it like this to simplify expressions, but it's a constant, multiplied by the scalar weight. And the scalar has this form. I dropped the theta and phi parts here for regularity conditions that I'm not going to go into, but basically what we're interested in is only when the scalar phi is time and r dependent. So it has this. And so if we do this procedure, we end up with a line element, which I wrote here, after some rescaling of the mass and time coordinate. So we do this so that the TT component is exactly the same as K. Okay, with a real
putting the arbitrary constant phi.
So we didn't try that because we just tried the simple case basically, which already asks a lot of questions that we don't have the answer to. So we didn't.
But I think it is possible.
You could, yeah. I mean, you can do whatever you want.
So that mainly
yeah. So you can do transformations of this form, and you'll stay within those. This is generic. And actually, what happens if you change the dependence of the coefficients here is that you either there are basically three subclasses. You have Horndeski, beyond Horndeski, and another one, and you can jump between them by gradually allowing X dependence. Basically, if you have no kinetic term dependence here in both of the coefficients, you actually stay within the Horndeski class. So you never introduce higher derivatives in the earlier ground equations. Then if you add X only in the disformal part, you have beyond Horndeski, and X everywhere, you have even beyond Horndeski. But yeah, in principle, you can generalize the metric. Sorry. Right, so this is the line element we obtain, and you can see here in orange, I put some parts that are new compared to Kerr. Here. And this, I put everything in orange because we'll see it's a very important term, because it's an off-diagonal term that, as I'll explain in the phone, we won't be able to eliminate. Okay, usually for Kerr or Schwarzschild, whenever you have dTdr term, for instance, in Eddington-Finkelstein coordinates or the such, you can always, so in the Kerr case, you can always eliminate it in order to have only one off-diagonal component, dT/d5. And in Schwarzschild case, you can, of course, diagonalize the matrix. In our case, we'll see that we won't be able to do this without introducing other off-diagonal components, for instance, d theta, dt or something. but I'll give more details of this in the final. And I'd like to say that, first of all, the trivial case A equals 0. So if we start with a Schwarzschild black hole here instead of Kerr, and for this A, we actually just map Schwarzschild to a new Schwarzschild black hole with a redefined mass. So the case A equals 0 is not interesting at all. We don't obtain a new black hole solution. We just get Schwarzschild with a new mass. So we'll assume that A is non-zero in the final. And of course, this formal parameter D is non-zero. Otherwise, we stay with the Kerr. The first thing to say is that the solution is regular. At least it doesn't introduce new singularities compared to the Kerr. And you can have hints of this by calculating some curvature variance and seeing that they only diverge at rho equals 0, just like Kerr. But of course, this isn't sufficient. You have to isolate a coordinate system where it's clear that the metric is regular. And you can do this by redefining coordinates like that and checking that each metric component only diverges at this rho equals 0. And in these components, these coordinates, the scalar field is regular here for r larger than 0. Sorry, there's a question.
No. Do you have some questions? Or is it just a noise? Oh, it's Sergey Larin, probably. So it's Sergey, do you have a question? Because we don't hear you. We hear only noise, some noise. No, he's not switched off, but Sergey, do you have a question?
No, thanks.
Ah, okay. That's just, well, I'll just mute you. Okay.
Sorry, okay.
Oops.
Right, so the metric is regular, at least does not use singularities compared to Kerr, but one major difference, as you can see here from the explicit expression of the Ricci scalar, when D is non-zero, is that the solution is not Ricci-flat. So this is very much different from DR. And the fact that the scalar field here is regular has some interesting properties linked to it, because I briefly mentioned that the scalar field has a constant kinetic term, which, in other words, the gradient of the scalar field is an everywhere time-like vector field. And there's a theorem that the existence of such a function, which in our case is the scalar field by itself, leads to the stable causality of the spacetime. This is a very nice property because it means, I mean, it's thought to mean that it's a necessary condition is not to have closed time-like curves in the region where the scalar field is regular. And this is nice because in some of the ad hoc deformations of Kerr that I talked about in the introductions, you often end up with such causal pathologies. So, for instance, closed time-like curves in the region which is outside the event horizon. Of course, we want to avoid such time machines. This is a nice property of our solution.
When you want to avoid closed time-like curves, time machine. When you want to avoid when pathology, time machine.
Well, just want to avoid time machines, no?
Not necessarily. I want to avoid, yeah, so I want to satisfy experimental data. There is no experimental data that there's no such time machines.
Okay.
There should be some other pathology, some inconsistency or something.
Well, okay, then with our spacetime, we can't test if there are actually time machines. I mean, we won't get time machines. But I thought this is like something we want to require. So
there was the opposite activity. Some theorems that time machines do not exist in usual fields, like if you do not violate the energy conditions.
Yes.
But actually, people wanted to make a time machine. Why not? and we somehow want to avoid it. And probably avoid it. I wonder why.
Well, yeah, I just started violating because I was just travel to the past.
Global.
Yeah.
Okay.
No.
Yeah.
Okay, I don't know, but anyway, we don't have time machines, and this is maybe it's bad for some people. I mean, for us, it was a positive one. Yeah. Anyway, because of the existence of this time-like gradient of the scalar field inherent to our construction, we have this property, okay, which is thought to be sufficient to avoid time machines. So now when we come to we think very important property, which is very different from Kerr, coming from the circularity conditions. So first, let me say that the spacetime is still axisymmetric, meaning that we haven't introduced any time or phi dependence of the metric components. And okay, these vectors still commute. However, now so again, lower the indices on these vectors and calculate the switch product, you see that it's no longer zero. And this was one of the necessary conditions for circularity. Which, okay, of course, when D is 0 or A is 0, you recover. But in the general case, the metric is non-circular. And this means that we can't write it in a form that, of course, you always have these two coordinates which are related to the Killing fields. And as we saw, for instance, in the Kerr spacetime, you could also always write it in the Boyer-Lindquist coordinates where you could do this simultaneous flip of T and phi, which left the metric invariant. And what we find in our case is that you can't write it in such a form. And if we go back to the full expression here, the term I highlighted in orange, it means that you can't remove this term, because if we were to remove it, then we'd get a circular form. Okay? So if we remove this, we have to introduce another term which violates non-circularity. So either a dt d theta or a d theta d phi or whatever. We can't just remove this in the usual way as in GR. And actually, the different parts, the thing that's different compared to GR is the theta dependence here in the TT component, because what you usually do to get rid of this dTdr component is redefine time with some new time plus a function of r dr, basically. And you can't do this here because if you assume that the function of r in the redefinition doesn't depend on theta, and you solve, you obtain something which depends on theta with this theta dependency. So it's just inconsistent with basically you're not doing a diffeomorphism, so you're not allowed to do it. And you can't remove this. So this is very much different from Kerr. And unfortunately, it has an impact on the separability structures of space-time. So basically, in our case, we no longer have a non-trivial Killing tensor, which makes the study of geodesics much harder because we can't integrate. I mean, we still have second-order coupled equations for the theta and r part of the geodesics equation. And this makes it difficult to solve. Of course, in the Kerr case, it's very much simplified because of the existence of the Carter constant, which separates the r and theta parts. However, the property is still interesting because you can, in principle, even get such solutions in GR, for instance, with original flows of matter. And in modified gravity, this ansatz, namely the circular ansatz, which is usually just assumed in the literature, when you have an axisymmetric solution, you always kind of assume that you have this reflection symmetry. In the numerical simulation of black holes in some classes of modified gravity, it was shown to fail, actually, this circularity condition. Which suggests that such solutions may be like a generic feature of modified gravity solutions. Or in other words, it's not maybe a reasonable assumption it's not reasonable to just assume circularity from the start in the context of modified gravity. Right, so now let me come to the study of hypersurfaces. So in the same way that I talked about Kerr a few minutes ago, let me start from infinity and go closer and closer to this object we constructed. So the first thing to note is if you go very far away asymptotically and compare the spacetime to the Kerr solution, you can actually, looking at it from far away, you can think it's Kerr with a redefined mass and tilde here. which I've already defined, but also here from the T5 component, you can read the spin, with the physical spin. Okay, so if you just look at this from far away, you just think it's Kerr with these parameters. So from far away, it's the same as G. Now let's zoom in a little bit. Let's define stationary observers again, like we did before, and go closer to the object. So you again have, if you want these stationary observers to be time-like, you again have the sort of static limit or ergosphere, or ergosurface, the surface of many names, when the time component of the metric vanishes, and inside which you need to have a co-rotation with the black hole here. So this function needs to be about for time-like observers. Now, so up to now, it's very similar to Kerr. You have this surface. But the difference now comes when this argument to the square root becomes 0. So in the case of Kerr, this was the outer event horizon. But in our case, this happens when this is verified. Okay, so it's a function of r and theta. So it's going to be a theta-dependent surface again. And if we can solve this equation and find the outermost surface, which verifies this is what we'll call the stationary limit. So it's just the limit for the stationary surface of this one, right? So this is our equation, and when d is 0, so if you kill this term, as I said, you recognize the equation defining the horizons for the Kerr solution. So you just get the largest root of this polynomial is just the outer Kerr horizon. But and yeah, so in the Kerr case, it's the event horizon, so it's a null surface. Okay. In our case, if we look at the nature of this stationary limit. So you define the normal vector to the surface. Here, R0, the surface, the station limit is defined by R equals R0 theta. So you can define the normal vector like this and calculate its norm. And you find that the surface is time-like, which means you can cross it in both directions. So it can be an event horizon. So in the general case, this surface, which in the Kerr case corresponds to the event horizon, is a time-like surface. So we haven't reached the horizon. It's not possible because we need a null surface for that. And a very interesting property is that because we basically built the surface looking at vectors of this form, and the Killing vectors of our spacetime, which can be written like this with a constant function here, a constant coefficient here, right? By construction, they're all going to be space-like inside this surface. Okay? So basically, we've reached a surface where inside which we have no more stationary observers. All the Killing vectors are space-like, but it's not the horizon. So it means that if we go deeper and find an event horizon, then the horizon cannot be a Killing horizon. So in this sense, we don't have the same property as GR, which says that all the event horizons are actually time horizons. And this comes from the fact that we no longer have a Ricci-flat spacetime. Because of the scalar field, this property is violated. And as I'll briefly state, this is one of the open questions, is the thermodynamics of this black hole. Because we don't have this rigidity theorem, which really simplifies the question in GR. So, okay, we've defined the static surface, the stationary surface, and now we go even deeper, and we need to find a null surface in our spacetime. And to do this, we need to define surfaces of this form, so with a theta-dependent profile, and define the normal vector here. And a necessary condition for the event horizon is to have this vector be null. Okay. And this leaves the following equation for the profile R of theta. Now, if we're looking at the Kerr spacetime, we don't have this term, and it's a reasonable assumption to look for surfaces of constant R. Okay, so if you have Kerr and you get rid of the last term here, you can also assume that there's no theta dependence, and in the end, you have to solve this polynomial, which has roots of constant R. So you haven't violated your initial assumption. So everything is coherent, and you find the event horizons in the Kerr space. Now, in our case, it's more complicated, and this is actually a common mistake in the literature. There are many papers which don't do this carefully. If you just solve this part here equals 0, or in other words, GRR upstairs equals 0, to find the horizons, the very first assumption when you do this is that you obtain constant par solutions, right? Because solving this GRR upstairs equals 0 means that you've considered a normal vector to your surface with 0, 1, 0, 0. So you've basically assumed your surface will not be theta dependent. So if we assume it's not theta dependent in our case, so we don't have this derivative part, and we solve this, we obtain roots which are theta dependent. First, this is incoherent, and which means that in our case we have to have this derivative, and it makes the problem much more complicated, obviously, because instead of having a fourth order polynomial here, we also have some derivative. And we can't solve it analytically, so we tried some numerical. We tried to solve it numerically. And in order to have a smooth solution, we also would like to have the derivative of this function r to vanish at the poles and the equator. So if we solve it numerically, and okay, we subtract this solution with this constant value, which is the value of the poles basically. So the poles theta equals 0 here, and we have 0. And then this is how much the numerical solution deviates from this constant value. Okay, and this is the equator part of it. And we see that, so in the full line here, for a given rotating value of the original solution, we vary the disformal parameter. So each plot here corresponds to varying disformal parameters. The dotted line is the stationary limit, which is not the horizon, right? And the full line is the solution to this equation. And we see that actually, in many of the cases that I plotted here, there's some sort of knee in the horizon, right? So the solution is not smooth. Maybe pointy here. And it's linked to the fact that these two curves need to touch at the horizon in order for the transition to be smooth. So for instance, this case in black here, we said, is not interesting because we don't have a smooth profile. And basically for a given disformal parameter, this means that there's a maximum rotation that we can attain in order to have a smooth profile. You see that these seem compatible. So for a given d, we can rotate much faster and still get a smooth solution.
So you have a constraint on the environment of the
Right.
What is the constraint? 0.9.
Okay, so let me the next slide kind of discusses this. So you can, if you tailor expand this equation now around the poles and the equator, you can actually find necessary conditions on the spin A, so that the Taylor expansion makes sense. Basically, it's linked to the fact that the second derivatives must be real. At some point, you have some square roots, and you want them to be real. And in both cases, you can find some limiting rotation. So in the case of positive d, there's some profile here which decreases. So if you increase the disformal parameter, there's a maximum rotation you can have in order for the profile to be smooth. Of course, for the Kerr metric, you find the maximum rotation 1, okay, for the extremal Kerr macro. And in general, these are necessary conditions coming from the Taylor expansion. That doesn't mean they're sufficient, but we did check numerically that the transition seems to be smooth for the values calculated here. So there seems to be, at least numerically, by increasing the precision, it seems to correspond to these bounds found analytically. So if you take the derivative of the equator for a given d, basically, and increase the rotation, you will find that at some point when you solve it numerically, it will become inconsistent with the zero derivative. And the point where it starts to diverge is precisely this curve. So it seems to be in accordance. And in this way, we just found for a given disformal parameter some maximum rotation that we're allowed to put in order to have a smooth profile of the solution. Now, in order to maybe convince ourselves that we've actually found an event horizon, we also constructed a family of surfaces starting from the numerically obtained horizon null surface profile with a family of surfaces depending on this parameter zeta here, where we examine the nature of these family of surfaces, and what we want to find is that for positive zeta here, there will be time-like surfaces, and when zeta is 0, we get the horizon, which is null by construction, and we want to find inside this horizon surface that there's a region where this family of surfaces is spaced out. This is exactly what we do for Kerr. You construct this family of surfaces and check that there is this change of nature of surfaces. So outside the horizon, the constant order surfaces are time-like and become null, and space-like between the horizon space. So there's a region like this where there's space-like. And again, we check that this is the case. So we're pretty much convinced now that we actually have an event horizon, but at least we do have a null surface. So yeah. I guess the important point here is that this stationary limit that we defined here is not a null surface and hence cannot be the event horizon. And this is the main difference with Kerr. And this is some schematic plot. As in Kerr, you have this red surface, which is the ergo surface. Okay. In red, you have the ergo region, and now the main difference from Kerr is what I plotted in green here, and what we call the stationary limit. Because as I said, in the case of Kerr, the black and green curves, black is the event horizon, are exactly the same curve. But in our case, there is this difference, the curves, even though they meet at the poles and equator. There is this small region here between the green and black curves where, I mean, which is new, and we still are a bit confused as to what happens because, okay, it's linked to the fact that, as I said, this black surface can't be a Kerr horizon, and inside this small region of space-time, all the Kerr vectors are space-like, but yet we haven't reached the event horizon. So we're still not so sure what this means, and this is part of what I plan to look at. Okay, of course, inside you have the wing singularity, that doesn't really matter. And finally, well, for this part, I just want to mention that, so in our construction, we have two bounds for the disformal parameter, the positive bound being plus infinity and negative being -1. So in our construction, B has to be in this bound. But we constructed the metrics, which are obtained by taking the limit in both cases. And what we obtain are simpler versions of the disformal spacetime, but which still have many of the interesting properties of the general case. So we believe that these, the two metrics I present right now may be helpful in understanding some of the properties we're wanting. So the first example is in the case D goes to infinity. So by defining this physical spin parameter, chi-2, which is the physical spin over physical mass. Remember, these are the quantities I defined from an asymptotic expansion of the metric. So basically the spin and mass that an observer from very far away would think that this is a Kerr black hole with this spin and mass. And after a suitable coordinate change, you can write what we call the non-circular short-term metric in this form. So when chi tilde here is 0, of course we have the short-term metric and the usual short-term coordinates. But in general, you have these off-diagonal terms here, dt d5 and dr d5. Of course, if this term wasn't here, you'd have circularity because you can shift these two coordinates. You can flip them, and because of the square here, you get the same metric. But in the generic case, if you flip tan phi, of course, this will introduce, this won't be invariant. So because of this term, we have a non-circular spacetime. But it's much simpler than the general case. And yeah, it may be useful in studying some properties. One simple calculation you can do with this spacetime is, for instance, calculate the Petrov type of the metric. Because as you can see, this is immediately rewritten in terms of some tetrad, right? And by building the Newman Penrose formalism, by constructing the null tetrad and calculating the vowel scalars, you can actually define two scalars which are invariants of the choice of tetrad. Because generically, the valid scalars depend on the null tetrad that you choose. But these I and J are invariant under that, and you can calculate this ratio, which was defined in the speciality index, and which tells you that when this ratio is equal to 1, the spacetime has to be algebraically special. So anything with type 1, basically. And in our case, we see that, so of course the expression is complicated, but I expanded it for a small span parameter here. You see that it's not. So I dropped like this completely general. And the other case that we were interested in is the other limit, and d raised to minus 1, which looks like a singular limit, but we were able to make sense of it in some way. But anyway, this is what we obtained in the end. And this is interesting because the physical spin that you read from far away is actually 0. You have no dTV5 and yet you do have modifications coming from the theta dependencies here that may yield some interesting properties. And again, here you can't diagonalize the metric because of the theta dependency. That's what I explained earlier. From the usual time goes to time plus function of RDR shift that we usually do. And because of this theta dependence, you're stuck with these non-trivial components, basically. So yeah, these are just two simple examples that we hope to study in more detail.
Yeah, okay, so how this, you have this formal transformation, GNU minus DU5, DU5, and efficient equals to D divided by Q squared.
Yes.
What is Q?
Q is so it's basically the norm of the scalar gradients. So if you, right, so here it's a constant in front of phi. And if you calculate the gradient of phi squared, the norm of the d phi squared, it's minus Q squared. So there's some constant in front of phi. So it's just, you see that since phi comes with a Q in the resulting metric, you will have only D. If you don't put Q squared here, you'll have D over Q squared, D over Q squared. So I just defined it this way.
Let me ask you a question. How this parameters tend into the Lagrange? Obviously, they enter the combination D over Q squared into the Lagrange algorithm. Yeah?
Right.
So you have another Q somewhere else in the Lagrange of the Q5 or
I don't really see what you mean.
why don't you have D over Q squared everywhere in the network? Where do you have Q without D?
Well, yeah, only in the scalar field.
So Q is a prime in this
Yes. Well, yes, it's the norm of the gradient of phi. I don't know.
Probably Q squared. The logarithm of phi is D phi squared Q squared.
No. It's just d phi squared.
Squared.
You're wondering what? Yeah, the logarithm I see what you mean now. Yeah, you get, in the way I wrote it here, you'd get, but I guess, the Lagrangian also depends on x. So basically, so Q squared is x, is what I call the kinetic term of the scalar.
Okay, so real disformal transformation is unified by x.
Well, okay. So generically, x doesn't have to be constant, but in this particular solution that we start with, and actually even in our solution, x is a constant, which is minus Q squared. But this is it doesn't have to be. Sometimes you have x which is non-constant. In our case, it is, and it's precisely this value.
So that's why I think that's separate. The logarithm of phi equals to minus Q squared. Right?
Yeah, if you replace if you replace the explicit values. What was I? Right now, okay. So this wraps up the part about the new solutions, and we still have open questions, namely what's the temperature of this black hole, and what's new, or can we have any nice features of the region here in between the green and black ones. And then another paper we did. Let me finish. I don't know if I still have a little bit of time. Yeah, in the second paper, we wondered what would happen, because as I mentioned in the introduction, the orbit of stars around Sagittarius A star have been studied for more than 25 years, and in particular, the orbit of one star, S2, which some groups, in particular the gravity collaboration, have observed for more than 25 years, and this means that it's done more than one period. And last year, they were able to measure the total precession. So the precession of the pericenter predicted by general relativity. And so we're starting to get data from the orbits of these stars. And what we tried to do is to study the orbit of stars around. So basically, we assumed that the Sagittarius A star is a disformed Kerr black hole, so the objects we constructed. And using the oscillating orbit method, we looked at the secular variation of the parameters of this ellipse here. So our star here is S, and its location is located by, so there's a fundamental plane here in gray, and you have many angles that you can, so the nodal angle omega, inclination angle delta, lowercase omega here, which locates the pericenter, basically give you the position of your star, and you can look at the secular variations over a long time, how these parameters vary. So for instance, general relativity predicts that the pericenter angle is going to change over time. And in the future, we will also be able to probe the variation of the nodal and inclination angles, which can give you actually the value of the spin and quadrupole moment of Sagittarius A star, and provide a test of the important no-hair theorem in GR, stating that all the higher order multipoles for a non-charged black hole are uniquely determined by its spin and mass. Okay, so you have no new parameters. If you meaning the mass and spin of a Kerr black hole, you know everything.
Can you simply calculate the TPM parameters, and then the experimentalists they will measure the experimental data and constrain these TPM parameters, so you will compare.
Yeah, this is pretty much what we did. I mean, it's through PN expansion.
Yeah, but you calculate the directly experimentally measured quantities. Why cannot you? Any parameters is deviations by TPM parameters, the standard TPM parameters. There are kind of rules. Null Surface, you might have 3, but experimentalists they constrain these parameters for the experimental. So this is
of course, no, I see what you mean. But in modified gravity, in these general scalar tensor theories, I don't think there's a simple way to do this.
Which are different from kind of different types of TPM parameters.
Yeah, I believe you're not really in the general construction of this TPM. So the standard, for instance, in the standard scalar tensor theories, the old Vatsky, the simple Vatsky connection, we have these parameters alpha, beta, which depend on the value of the scalar field, basically. But in our case, I don't think you can do it so easily. I forget why not. No, I see what you mean, but
it's not to parameterize your effects of your new gravity of orbit by now TPM parameters. So to say what is the values of TPM parameters which will give the same effect. Yeah, I got what you mean, but you are telling me that you can parameterize all effects of your theory with the Euclidean parameters, even the differences. That's all those things.
Yeah, this is what I think.
For circular or for elliptic orbits, you can, for almost elliptic orbits, you can parameterize your effects, or you have some different effects, which can be.
Yeah, okay, I'm not sure, but maybe we could have done something simple. I don't know. Yeah, so sorry. So what we do basically, so we do this expansion to 2p order, so the second Hamiltonian, and you find the secular shifts of all these functions. So the semi-radius vector of the ellipse, alpha beta here is just eccentricity and pericentric angle, inclination angle, label angle, and everything that's not in orange is up to 2p order is exactly what's predicted by Kerr. So basically, the only thing we get in general case of our metric is some rescaling here, which amounts to a rescaling of the quadrupole values, basically. And what this means is that the quadrupole, the no-hair theorem, when our disformal parameter is on 0, is violated. So if in 10 or 15 years, I don't know, experimentalists measure the spin and quadrupole moment and verify the no-hair theorem, at least for the quadrupole, then this basically at least puts severe constraints on this disformal parameter. What we tried to do also is to, because okay, what I wrote here is the generic case of the disformal parameter. We see that this 1 plus b actually appears the denominator. So if b is constant, but if you take the constant to be very close to -1, you can expect that higher order terms in the metric maybe will influence some lower Hamiltonian terms. And this is what we did. We tried to take b very close to -1, so parameterized by this Hamiltonian parameter, basically, which here is a constant. So if we take the example of S2, it's basically the mass over the semi-major axis of the star S2, and parameterize d like this. And if we do this, we see that actually even the pericenter shift is changed. So as I said, these effects here are actually brought 1 order higher right here, and can change the prediction for the pericenter shift. So this gives a constraint using the experimental measurement of the gravity correlation. This gives a constraint on this parameter lambda here. And if we know the spin of the black hole, which we don't yet, if we do, it also gives a lower bound on this disformal parameter. Basically, we can't choose it too close to -1, otherwise it wouldn't be compatible with the gravity measurements for the S2 stuff. And what you can do is, using this bound, you can actually predict so assuming that this is for the S2 star, you assume that this is the maximum, or let's say the minimum value closest to -1, which verifies the gravity measurement. So you call this d0, take this value, and then using this maximum deformation, you can predict what the shift for another star, which may be observed in the future, will be. So you obtain this value, which is some prediction. And because of the fact that this parameter epsilon is a constant here, it's not just the usual Hamiltonian parameter, which is a function of R. What we wrote here is only valid for certain stars which have roughly the same basically distance or ratio of mass to distance as S2. But if we find an orbit of a star that's similar to S2, then this prediction would apply and constitute some prediction of this modified gravity outcome. So let me conclude. So basically we constructed deformations of Kerr, which unlike the usual objects in the literature are actually solutions to scalar tensor theories. So we know the theory, and which present many interesting properties, among which non-circularity, which we believe is really the new feature that's very rarely discussed in the literature. And usually people assume circular spacetime, but as I tried to explain, this assumption is not necessarily valid in modified gravity. And has two very important properties, among which the fact that the horizon is not located at constant r, is not occurring horizon, and this splitting of the stationary surface and the event horizon that I discussed, which is still very enigmatic to us. And I just explained, we also looked at the secularization of orbital parameters and saw that, okay, in general, the Kerr theorem is violated, but also if we push this disformal parameter to be very close to -1, we can predict some signature of modified gravity for upcoming measurements of stars around Sagittarius A star. And let me end by saying that these objects have been studied by other groups. Very soon after our paper, another group gave more details basically on the specific theories that these objects solve. But later, some groups studied the shadows of this black hole. So as I said, the study of GD6 is not easy now. But this group did it a little bit to look at the shadows of the black hole, and also more recently, kind of using the same idea that we had for the stars around Sagittarius A star, the group tried to test non-circularity effects of pulsars, using pulsars orbiting Sagittarius A star. And there was also other papers that been mentioned, but we believe it's an interesting subject to study. So thanks for listening.
Thank you very much.
So I don't know.
Okay. Do we have questions? Oops. More questions?
About the constraint on just d close to -1.
Please.
I wonder whether you already have a constraint, because you've shown that the maximum speed, right, somewhere about 0.4 for collision.
Okay, this is something I didn't give details about, but basically this plot is using the parameter A here. So, okay, something I didn't really mention is that for simplicity, using this parameter A, which is the spin of the original object, so in the Kerr metric here.
So A is not the real spin.
It's not. It's the real spin is this one, and you see that actually when D, yeah, I guess the spin goes to 0. Yeah.
Okay. So you don't constrain this spin from D to 1 spot.
Actually, that's a good point because wait.
So my question was to speak about my question is that from measurement of the shadow of the hole in M87 or something, there was a spin measurement, right?
Right. So at some point we looked at this M87 papers trying to get constraints, but what we found is that what they constrained was only linked to like the spherically symmetric law. It wasn't really linked to rotation. So in our case, we weren't really able to constrain this one object because, as I said, when we start with a Schwarzschild solution, we just stay with spherically symmetry objects. So we don't really get in physics. But yeah, I think our conclusion was that with M87, for the moment, we weren't able to say anything. You're saying
they're saying the spin of the black hole equals to this.
They're saying they have the spin.
They kind of.
Okay,
Maybe I don't remember. Yeah, maybe I don't remember, but they kind of constrain the spin.
Okay.
No.
Maybe I thought. Okay, maybe there's a paper, but maybe we thought it wasn't precise or something. I don't know. I remember we briefly looked at these papers.
So this is just a question.
Yeah, no, I think our conclusion is that for the moment with M87 we can't say anything. So maybe, yeah, but I forget. This is a long time. Sorry.
Any more questions?
Maybe some questions from Zoom.
Okay, if there are no more questions, let's thank the speaker again.
Turn this off.
Yeah.
Okay. Thanks for the seminar. You've seen it twice now. You're a specialist.
No, I've seen it in the internet previously.
I know this is
Because it's much better.
Yeah.
So you want the question?
Yeah, sure. Maybe.
So you did the seminar and
I did, yes. I've basically what I'm working on now is not working, so I can't present it sadly.
okay.
So as I said, the paper was out like a year ago. So it's the third time I give this talk. I mean, to people in Russia, basically.
I see.
So I gave it at ITMP also last week.
Okay.
So let's do that.